Hello, we are the CLAWS team from the University of Michigan. We'll be presenting our work on ATLAS. CLAWS is a collaborative lab for advancing work in space, which creates human-centered, software-driven applications to further humanity's presence in space and streamline mission procedures. The team is a multidisciplinary group of undergraduate and graduate students from across the University of Michigan, divided into sub-teams to handle various aspects of the project. My name is Riley, and I'm the CLAWS team lead. I'll be giving some background. Before returning to the lunar surface, sampling, task management, navigation, and planning would all benefit from next-generation technology. The goal of our team's efforts on ATLAS is to create a solution for these unique problems of planetary exploration and support research for NASA's Artemis program. CLAWS participated in both the NASA Suits and NASA XHAB challenges. The two aspects of the Suits RFP which especially stood out to us were granting astronauts independence and equipping them with tools tailored to the lunar environment. The XHAB challenge sought to implement these same ideas into this analog field trek setting as a practical demonstration. We are not the only people working on this problem, and we've sourced a lot of inspiration from the other AR projects being developed in industry. Our team has specifically referenced the HoloSextant and Jarvis throughout the development process.
Hello, my name is Sahil, and I'm the system administrator for CLAWS. I'll be going over the architecture of our solution. In response to the RFPs, our team decided to focus on making exploratory tasks, such as navigation and sampling, easier by creating a flexible and non-intrusive toolkit. We call this system ATLAS, the AR toolkit for lunar astronauts and scientists. ATLAS interfaces with an external server that hosts the CLAWS Mission Control Center. This enables an exchange of information during EVA operations and allows for mission data to either be transmitted to the HoloLens or reviewed later by Mission Control Center operators. To support all of these objectives, we put together mobile support equipment. This includes a suite of external sensors connected to a Raspberry Pi for data storage and processing. To address the drastic changes in lighting in a lunar environment, we have included an external lighting source that is activated by photoresistors. The building blocks of the ATLAS infrastructure are protocols and modules. Each protocol is designed for a specific mission state and has modules which provide the core functionality for each task. In addition, utility classes contain general use functions to streamline development. The protocol manager runs at startup and ensures smooth transitions and continuity between protocols and their modules. Here we can see an example of the sample collection protocol broken down into the various modules and utility classes that it leverages.
Hello, I'm Rupal, the administrative lead, and I will be going over some of our protocols and modules. For our navigation protocol, our goal is to provide guidance through waypoints while minimizing obstruction to the astronaut's field of view. In addition to the general use case waypoint, we also have special classes for landmarks, sampling sites, and hazards. Astronauts can receive navigational guidance to all types of waypoints. Additionally, they can set waypoints at their current location during an EVA. Here's the data structure of a waypoint. This metadata gets captured whenever a waypoint is set either by the astronaut or by mission control. For the sampling task, our goal is to support and augment planetary science operations through geonodes. Geonodes consist of sampling specific mission tasks, associated imagery, audio recordings of voice notes, and QR codes of the sampling containers. Each geonode is associated with a waypoint that marks the sampling site. This information is then stored on the MCC and can be accessed easily during post-mission analysis. The primary way to interact with ATLAS is through voice commands. Our naive solution is through Keyword Recognizer, which maps specified words or phrases to different functions in the backend. However, we can improve upon this solution using conversational AI. Our smart voice assistant, VEGA, is built using an open source platform which handles the natural language processing for us. We can currently provide information about biometrics and plan to extend VEGA's capabilities to include navigational guidance in the future. On the right is a sample conversation an astronaut could have with VEGA. They can ask about their heart rate, whether there are any warnings, and how long the water supply is going to last.
Hi, I'm Caesar, the Mission Control Center lead, and I'll be giving an overview of the MCC. The MCC is a web application that relies on a Django web framework and a PostgreSQL database. This serves as a central hub that will be used by everyone on the team in every stage of the mission. So before the mission, the team can come together to view mission procedures and mark any important waypoints and areas on the map. Next, during DVA, the supporting team of mission controllers and scientists will enter the control room page. This is where they can see an overview of everything that's happening, including biometrics, communications, and geonodes. They can also modify waypoints and mission procedures, such as adding get-ahead tasks. Finally, after the mission is over, the team can go through all of the data that was collected and use this information to improve upon the next mission. Here's a look at our navigation tool. We're currently using the Bing Maps API to display all of our waypoints, which you can see in the list on the left. Here's a look at our GeoNotes tool. The notes are listed on the left side, and clicking on a note will pull up its details on the right side panel. Aside from the main mission-specific functionalities, the MCC also provides other miscellaneous tools such as mock telemetry and warning streams. For example, here's a tool to toggle different warnings that can be used during testing to see how our system reacts to different malfunctions. In terms of the overall design of Atlas, our philosophy centered around minimalism and uncluttered user interfaces. More importantly, the display needed to be readable in both bright and dark environments. We also wanted to standardize the design across different modules so that the overall system felt clean and intuitive. We kept all these ideas in mind while creating the mockups that you see here and on our next few slides.
Hi, my name is Emily, and I'll be going through an Adobe XD mockup of the Atlas application. At the upper left, the task list displays the ongoing mission and can expand to its full length to show previously completed and future tasks. The voice assistant VEGA serves as the information center, where astronauts can receive warnings, notifications, and messages. When inputting a voice command, a transcript is shown for confirmation and the associated action is performed. In the bottom left corner, the minimap displays the astronaut's destination, home base, and no-go zones. The user is fixed in the center and is always facing forward. When they turn, the minimap rotates around them for situational awareness. If an issue occurs with the astronaut's partner, their status will turn red, which can be further expanded to show the associated biometrics. To distinguish the current speaker, a mic will appear next to their name. Warning messages contain their cause and instructions to resolve the problem. Primary warnings are displayed in red and cannot be dismissed from view. Secondary warnings are displayed in orange and are stored as a small dot above the voice assistant. Astronauts are able to set waypoints at their current location through voice commands. The voice assistant guides the astronaut as they drop and name the waypoint. QR codes are assigned to individual sample containers. When a QR code is scanned, a GeoNote will begin. The voice assistant will display the GeoNote duration, the number of images taken, and a red dot indicating that note-taking is in progress. Once the camera is activated, the window will be wrapped in a green ring, indicating the camera field of view. After taking the photo, it'll briefly stay under the voice assistant before disappearing. And finally, for perspective, this is what our design looks like in the Microsoft HoloLens.
Hi, Riley again. I'll be talking about our team's future work. In addition to migrating our Atlas mockups to the HoloLens and conducting testing, we're planning to work on expanding the capabilities of these systems. This includes finalizing control room functionality for the MCC, building external hardware components, and integrating VEGA into Atlas. We also have 3 new projects planned for the future. The first of these is C3TM, which stands for Computational 3D Terrain Map. With this project, we will collaborate with the NASA Trek team to develop a wrapper for the Trek API. The API provides services such as lighting analysis and crater detection. C3TM will be used to package this data into 3D terrain objects, which can be integrated into systems such as Atlas. For the second project, we want to create a distributed lunar network of nodes using a peer-to-peer system of small and affordable radio towers, such as the one shown here. This system will be able to support multiple astronauts leveraging the Atlas system and relay information between them. The third project will involve incorporating machine learning into our biometrics module to model resource depletion on the fly. This idea originated from a meeting with former astronaut Dr. Jim Bajan. He suggested that using machine learning in this way could give astronauts and mission control a method for determining if biometrics are following an expected trend. Finally, we would like to thank all of our wonderful supporters, including our faculty advisor, Dr. Leah Sterling. And last but not least, thank you for listening. If you have any questions or would like to chat, please feel free to reach out to us.